per unit system applied to three-phase electrical power systems. Hello everyone, my name is Rafael. I am an electrical engineer, and in this video I would like to discuss with you the use of the per unit system in three-phase electrical power systems. And to do so, I chose this problem here. I am going to read the exercise and show you the solution. Let me do it. Per unit system applied to three-phase electrical power systems. The exercise: determine the voltage and the power at the load for the system of the figure in per unit. We are given this data for the generator, for transformer 1, for the transmission line, for transformer 2, and the load. And the problem wants us to use per unit. And whenever dealing with per unit, we need to establish base values. Base values for region 1, I'm going to call it region 1, the region of the generator. I'm going to call the region of the line region 2. And I'm going to call the region of the load region 3. First of all, region 1. For region 1, we are going to establish as base values the voltage VB1 as 13.8 kV, the apparent power (50 MVA), and with these values we can calculate the base impedance for region 1. We're going to use these values here, 13.8 kV squared divided by 50 MVA, and we find (3.81 ohms). Now let's do the same for region 2. For region 2, we need to look at the voltages of transformer 1. 13.8 kV, 138 kV. So the base value of voltage for region 2 is going to be 138 kV. The apparent power for region 2 is going to be 50 MVA. Observe here that we're using different values for the apparent power. We're using 50 MVA, but transformer 1 is rated at 20 MVA. There is a difference here. This difference is going to be taken care of. We are going to account for this difference in letter B. there will be some adjustment of this value here, the per unit value of the series reactance. We are going to have to adjust it. But for the moment, let's simply consider that we're using 50 MVA. And use these values, we are going to use this expression here to find the base impedance of region 2 will be 380.9 ohms. Alright? Now let's go to region 3. For region 3, we need to look at the turns ratio of transformer 2. The turns ratio A is equal to 140 kV divided by 30 kV, which is 4.667. We're going to use this value. Okay? Why? Because we used 138 kV for region 2. But transformer 2 is not rated at 138 kV. It is rated at 140 kV. We need to conduct some adjustments here. Then the voltage at the load region 3 will be 138 kV divided by which is approximately equal to 29.571 kV. Okay? Did you comprehend the adjustment? The voltage for region 3 at the load side is not precisely 30 kV. The voltage is 29.571 kV. Then the base voltage will be this. The base apparent power for region 3 will be again $50 MVA. Likewise, as we discussed before, transformer 2 is rated at 25 MVA, but we're using 50 MVA. It's different. It turns out that we are going to adjust this value here to use in the system. Okay? Because we're using for the system this base apparent power. But the transformer used this value for this reactance. Then to use the system, we're not going to use this value here. We're going to have to adjust it. because we're using 50 MVA and not 25 MVA. Okay? And lastly, we need to find the base impedance for region 3. This number squared divided by this, and we find 17.5 ohms. With these values at hand, we can come up with the per unit system. We can convert it all to per unit. As I said, as the per unit value of T1, transformer 1, was calculated for the apparent power of 20 MVA, and the reactance of transformer 2 was calculated for the apparent power of 25 MVA, and we are using for the system 50 MVA, we are going to need to adjust these values, and this adjustment can be carried out using the following expression. I'm going to put it here. Okay, what does it mean? It means that the reactance in the per unit system number 2 is going to be VB, the base voltage in the per unit system 1 divided by the base voltage in the per unit system 2 squared the base apparent power of the per unit system 2 divided by the base apparent power of the per unit system 1 and multiplying the equivalent quantity in the per unit system 1. Okay? We are converting from one per unit system to another per unit system. And to do this, we use this expression here. Okay? So the new value for this quantity is going to be this reactance in the adjusted per unit system is equal to 13.8 kV divided by 13.8 kV. We are not adjusting the voltage. The voltage is already what we wish it to be. Nevertheless, we are adjusting the apparent power because in the per unit system 1 it is 20, but in the per unit system 2 that we're using it is 50 MVA. This is an expression that we're going to use to adjust this value here. And then we find that it is equal to 0.2. We are going to use the same expression to adjust this reactance. Okay? Observe that T2 is rated at 140 kV, but we're not using 140 kV, we're using 138 kV. Then there needs to be some adjustment with the voltage. Observe also that here is 25 MVA and we are using for the system 50 MVA. Then we need to adjust the apparent power as well. Then the adjusted values will be, for this reactance, instead of being 0.08, it is going to be 0.2. And for this reactance, instead of being 0.06 per unit, it is going to be 0.122 per unit. And now we can create the model in per unit. But before, let's not forget, we need to convert this impedance and this impedance to per unit. For the line, it is going to be Z line divided by the base impedance for region 2, which is the region of the line. Using the values, we find Likewise, we're going to do for the load. Observe that now for the load, we use the base impedance for region 3. And if we use the value, this we find per unit. With these values here, we can create the model in per unit and eliminate the transformers. Instead of writing the transformers, we're going to use the reactances, not this, the adjusted values. And then our system is going to be this is the reactance of transformer 1. This is the impedance of the line. This is the reactance of transformer 2. And this is the impedance of the load. And there will be a current here. We are going to find the value of the current, which will be in per unit, not in amperes. The value of the current is going to be the division between the voltage of the generator in per unit by all these impedances here, when we carry out this division, we find this value here for the current. Okay? Have you understood everything? Now we are going to find the voltage and the load and the current in amperes. We are going to find the voltage and the current. Here the current is expressed in per unit. We wish to express the current and the load in amperes. at the load in per unit is equal to the current in per unit times the impedance of the load in per unit. This is in ohms. We calculated the value in per unit. Just use it and you're going to find and using the base value for region 3, if you remember we calculated it, we find that the voltage at the load in volts is 27.5 okay. This is the value of the voltage at the load, and the current at the load will be a very common doubt. The current in per unit is the current that flows throughout all the system, in all regions, in per unit. But in amperes, the current here is different from the current here, which is different from the current here, because there are transformers in the system. Transformers change the value of currents and voltages. So what we do? To calculate the current at the load, we can either divide the voltage by the impedance or multiply the current in per unit by the base value of region 3. We are going to simply divide V load by Z load. And then it is going to be the division between this value here and this value here. You can use a calculator and you're going to find here it is not in per unit. I made a mistake. Very good. This is not in per unit. This is in kV. Okay? Here is per unit. Here is kV. And if we use this value here, 27.5 in the phase negative 5.87 kV, divided by this, we find the value of and to finish, the real power delivered to the load is going to be we're going to use for V load this value, for I load this value, and the cosine of the angle between them, between this, and we find 12.3 megawatts. Okay, my friends, this is the exercise. I hope you enjoyed the video and learned from it. I am a teacher. If you want to book a lesson with me, use my WhatsApp number, guys. Goodbye!